Hey, APL class, we're going to finish up the last example. It has a few parts, but we're going to look at doing now actually finding the derivatives of some functions that involve the inverse trig functions that we have here. So this is, we've got the formulas here, and like I said in the previous video, they are a little bit cumbersome. They have quite a formula to them. They have a lot of parts in there. But what I want to point out is, one thing is that typically if you do see one of these questions on the AP exam, there's rarely going to be more than one of them, and they're usually going to involve either arcsine or arctan, likely not the secant or the cosecant, but not saying it couldn't happen. But so yes, if the question is do we have to memorize them, yeah, you have to be responsible for them. But I do want to show you a method that if you weren't able to come up with this out of the blue, you might be able to figure it out if you draw out a triangle and use implicit differentiation. So I do want to run through that. The other thing I want to point out is the formulas that are here are set up for if the function wasn't just arcsine of x, if it was arcsine of, let's say maybe it was x squared or 2x or something like that, then a chain rule would be involved with that. So that's why we're saying a u, so that we would take u prime over the square root of 1 minus u squared. If it were just the derivative of arcsine of x, then your u would be replaced with an x, and then so the derivative of x would become a 1. You know, so where we have u prime, we'd have a 1, and where we have u squared, that would be x squared, and so on. So I did write those out in terms of if they were just x instead of u, u representing some other function where the chain rule is necessary. So I wrote those out for the first the left side of these, so this arcsine, arctan, and arcsecant. I didn't write them out here because it's the same thing. You can follow the pattern, and basically these formulas for arcsine, arccosine are the same, with the hopefully you're seeing this pattern that when we compare derivatives of sines to cosines, they're the same, other than you have the negatives there, right? And so arctan versus arccotangent, same formula. It's just that the cotangent, all the cofunctions, when you do those derivatives, end up having negatives with the answer, right? Arcsecant and arccosecant, we just same formula, just negative. So anyway, I did want to just back this up real quick and say, okay, well, what if we did want to find the derivative, and we didn't quite have this memorized, so let's just start with the first one. And I'm not gonna, this is the only one I'll show, but there's a process. This process could be followed in a similar way for some of the others. So if our function was the arcsine of x, so if we're looking at y equals arcsine of x, and we're like, okay, let's do the derivative of that. Well, the problem is maybe we don't remember that formula. So what we could do is maybe rewrite. So the way we could rewrite this, since we don't want to have arc or inverse sine in there, we could take the sine of both sides of this equation, and that would give us sine of y. And then if you take the sine of an inverse sine or an arc sine, it cancels and just leaves you with that x on this side. Okay, so by taking the sine of both sides of the equation, then we simplify it to this, which makes sense. If x equals sine of y, then y would equal the arc sine of x. That would make them equivalent, right, just by doing the inverse operation to both sides. Okay, so now at this point we have an equation that we can take the derivative of both sides, because we know what the derivative of sine is and we know what the derivative of x is. So derivative of sine is cosine, so we're going to say it's cosine y and follow that with our dy dx, right? And the derivative of x is 1 dx, so that's just 1, right? Now if we solve that for dy dx, we could say that dy dx is equal to 1 over cosine of y. And that would be our derivative, but it doesn't look much like what we had here. I guess we have 1 over something, but we have cosine of y. Now, we want this formula in terms of x, right? And so what we want to do then is, can we find a way to write this in terms of x? Well, we have x up in this formula right here, right? So we're saying x is equal to sine of y. So let's build from that. And because we are talking about a trig ratio, let's say, okay, well, we use right triangle relationships with trig ratios. That's what we're most familiar with. So let's just say one of these acute angles, and I'll just pick this one here and see. Let's call that angle y, since we're taking sine of y, and what we're saying is that sine of y equals x. Well, that means that its opposite over hypotenuse ratio is x, or we could think x over 1, right? We wouldn't have to put a 1 there, but we want to label both as many sides of our triangle as we can. So our ratio x, just like what we did over on the above examples, we're going to say that the opposite side is x, and then the hypotenuse would be 1. And then using our Pythagorean theorem relationship, we know that to get that other leg, we'd have to take hypotenuse squared minus leg squared and take the square root of that. That would leave us with 1 minus x squared, and we would take the square root of that, and that would give us our other remaining side in our right triangle. Now, okay, so if we have that, we go back to what we found for our derivative here. dy dx was 1 over cosine of y, and if I want to replace that cosine of y with something in terms of x, well, I think I can do that now, because the cosine of y would be the adjacent side over the hypotenuse, right, which would be square root of 1 minus x squared over 1, and so I can put that right there, which is going to give me, so now my dy dx, if I have it in terms of x, would be 1 over the square root of 1 minus x squared, which is what our formula is. I did write it out with the in terms of x here, and it's the same thing. So if you could redo this process, if you forget, it kind of gives you a way out if you completely forget, what this formula is. Maybe if you start it, you'll be like, oh yeah, that's right. Okay, even if you start drawing this triangle and then find that, this piece, that might help you, remember what the formula is. And it could be done in a similar way for some of these others. Okay, but the easiest thing is going to be if you can remember some of these formulas, right? So as we continue going through these, if you know the formula, they're not hard to do. So if we're taking arc sine of 2x, and we know that the formula for that is going to be, u prime over 1 plus u squared, u being the 2x in this case, right? And oh, I'm sorry, that was arc sine, not arctan, my bad. Go up here. U prime over square root of 1 minus u squared, right? That's my formula. So I'll just write that here just so that we know what it is, but it'll make more sense when I have it written right beside the problem. So if I have that, and my u then is the 2x, so the derivative of 2x is just 2. So, and then I'd have the square root of 1 minus 2x squared, which would be 1 minus 4x squared. So when I square that 2x, I would have 4x squared. So the answer for this, just using the formula, just plugging in some values there, u prime over 1 minus u squared would be this. Okay. All right, so for the next one, so our formula for arctan, we know that one is u prime over 1 plus u squared. And so plugging in the values for that, I would have, so u being 3x, right? The derivative of 3x would be just 3, and then I would have 1 plus 9x squared on the bottom. And that would be my solution there. Okay, next one we're doing, and so yeah, your notation can look, a couple different ways if we have it like this. We know that means arctan or inverse tan. Right, so again, it's the same formula as we just did, u prime over 1 plus u squared. And so that's going to be, now the derivative of, if you recall, derivative of square root of x, you have to call it x to the 1/2, so we'd have 1/2 x to the negative 1/2, which when we simplify that would be 1 over 2 root x, and then I'd have over 1 plus square root of x squared, which just ends up being 1 plus x. So we probably want to clean that up just a bit. So if we were, complex fraction, if I multiply by the reciprocal of the denominator, I would have 1 over 2 root x times 1 plus x. And I guess that's probably simplified enough. I suppose we could distribute that through, but it might be left in the factored form too. Okay, here we've got inverse secant, which we haven't done yet. This one's probably lesser used, but our formula for this one is u prime over, then it was absolute value of u times the square root of u squared minus 1. Okay, so there's our formula. And so in this one, our u is the e to the 2x, right? And so we also have in this one, so this one's a little extra to it, because it's not only the derivative of their inverse secant of some u, but it's then the whole thing squared. So to start off with this, we actually have to apply our power rule. And when we do our power rule, we bring our two, their exponent's going to be multiplied down, and then we're going to leave, the inside piece alone, but then we have to multiply by the derivative of the inside piece, which is our inverse secant. So this has got a little bit of work to it. So power rule first, so 2 comes down, and then I've got secant inverse secant of e to the 2x, e to the 2x like this, and then I'm reducing my power by 1, so I don't need to really write a 1 for an exponent, and then times the inside piece, and now I want to multiply it times the derivative of that inside piece right there. And so if I apply this formula in there to get my derivative of the inverse secant part, so we know that that's u prime, u being this e to the 2x. So the derivative of e to the 2x is e to the 2x times the derivative of that 2x, which is 2. So it's going to be 2e to the 2x is what u prime is going to be for that part. And now underneath I'm going to have absolute value of u. Now that's to ensure that it's positive. Now since our u is e to the 2x, that really can't be negative, because a base that's positive, whether x's are positive or negative, you can't get negatives for that. So we don't necessarily need those absolute values. So we're going to have e to the 2x out here, and then we're going to have the square root of e to the 4x, right, because that's u squared. So if we had e to the 2x squared, that would give us e to the 4x. So I'd have e to the 4x right there, and minus 1. Okay, so there is that information. Now, we could, I suppose, we could leave it like that. If we wanted to, we could probably multiply the 2 and this 2, and then put that inverse secant in the numerator. It might make it look a little cleaner if I do that. So if I do that, I'd have a 4. In the numerator, I'd have a secant, an inverse secant of e to the 2x, and underneath I would have my square root. So I just want to point out here too, I did have e to the 2x, yeah, that's still there. Okay, and then underneath I'm going to have my square root of, let's see here. I simplified, did I skip something here? E to the, oh, I know, okay. So I wanted to point out here that when I put these together, and let me do this in a different color, I have e to the, this one cancels, I can cancel that one out right there, okay? So that'll just help clean it up a little bit better too. All right, and then underneath I'll just have the square root of e to the 4x minus 1. Be a little cleaner than what we had before. So there's my derivative. So that one's a little bit, it's got a bit going on there, because we had to do the power rule, and then with the chain rule involving the derivative of our inverse secant. But that's it. So there's our notes for doing some derivatives of inverse secants. Inverse trig functions, not just